Hi there. I first want to thank the team at Jump for inviting me here to speak today, and also for building a world-class product that has really and truly changed the way I look at the world. In fact, that's what I'm going to talk about today, how we can and need to reshape scientific experimentation for the 21st century. With help from powerful mathematical models and methods, and from tools like Jump and Riffyn Nexus software. In fact, I've dedicated the last 10 years of my life and career to the purpose of trying to reshape scientific experiment. And for the impatient, like me, I'm going to boil it all down to two simple things. First, experiments are measurements that generate data. And second, data is an asset for building models of the world. Sounds simple, I know, that's the point. But actually, from the earliest age, we're taught something different. We're taught and retaught that the purpose of an experiment is to answer a binary question. That it's to define the question as a provable hypothesis and then test it. In other words, we're taught that an experiment is a judgment process to decide if something is true. We're taught that it's not just the experimental method. In fact, we're taught it's the scientific method itself. And this approach has carried us far in society, but I think it's no longer adequate for today's science. It's not really how we learn things, and it's not really how we understand the world. Such an experimental paradigm, one that reduces our complex world to just a sequence of binary judgments, I think it does an injustice to the richness of nature's workings. Take weather forecasting as an example. You could run an experiment to answer the question or to prove that winter is colder than summer, but that's not understanding weather and climate. To understand is to be able to predict, and for that you need to measure and integrate massive data streams and mathematical models on the dynamics and heat and the activities of complex air and water flows across and between water and land masses. In short, to truly understand something is to build a predictive model of it. One with rich shades of gray and multitudes of interacting variables. One that can explain past observations and predict future behavior. And for that, an experiment must be a much richer tool, a tool for characterizing the multivariate complexity and continuity of the real world. So let me explain with an example close to my heart, one from yeast bioprocessing. This is the DSM Amyris plant in Brazil, which I helped to create some years ago. And those tall tanks you see, those are 3 of the 6 200,000 liter reactors carrying genetically engineered yeast. These yeast turn sugar, which you can see in the sugarcane backgrounds, the fields in the background, into a designer oil called farnesene. This plant runs the most advanced human engineered yeast and bioprocess in the world. It broke nearly all records and limits that every world expert on yeast said couldn't be broken. And along the way, there was some brilliant science and engineering that used really sophisticated data tools, including Jump, to deliver those innovations. And one of them, my favorite in fact, was to just add water. Just add a little more water to the reactor and you get 5 to 10% more product out. Let me briefly explain and show you how this came about. So what you see here is a collection of data points from a single experiment, plotted on the axis of product yield versus a particular parameter. There really isn't a whole lot from that experiment to see or conclude. But when you combine 500 different experiments together in a single aggregate data set, not one of those experiments of which was designed to test this particular parameter X versus yield, you find something really extraordinary. That aggregated high-quality set of data revealed unexpected correlations, which you can see by that trend line, that regression line. This stacking of measurements together unearthed a critical model of yeast physiology, and when we combined that model with another model, a physical model of reactor dynamics, it predicted that if you just add a little bit of water to the reactor, you get more product out. this is the prediction from that model. The red line showing that incremental improvement in reactor productivity. And guess what? It worked at 200,000 liter scale, in fact, and it saved millions of dollars in production costs. And if you buy a little bit of Amyris's Biossance cosmetic products today, or if you take vitamin A made by DSM, you're getting a little bit of the benefit of that optimized plant yourself. So good experiments are a measurement of natural law, not just simply a judgment of whether a question is true. A successful experiment generates a rich tapestry of reusable information, multivariate information, not just binary answers. And maybe this seems kind of obvious or philosophical navel gazing, but it's not. The implication is profound. Consider this analogy that I've shown here. A caliper versus a car race. The caliper is a measurement. It generates data about matter. A car race is a judgment. It resolves a postulate. If you compare the two, you see, and you think about a caliper as delivering multivariate information about different aspects of what you measure. The car race is binary. A measurement is permanent and absolute. A judgment is temporal and it's relative to the comparison you're making. And a measurement is a building block for predictive modeling, whereas a judgment is a building block, frankly, for belief and confirmation, validation of belief. And that last bit here, the building block for predictive modeling, that's the key point. That's the key difference between these two approaches to experimentation. As Sidney Brenner once said, who is a Nobel laureate for discovering mRNA, he said, a good measurement generates complete, accurate, and permanent data. Data that's a reusable asset that can be extended and built upon to assemble a full understanding of natural law, a predictive understanding.